Okay, there we go. Um, now I lost my train of thought. But we are speaking, just to make sure there's context to what we're talking about now. We're speaking to the angle bisector. That was a take-home exercise, not necessarily not a graded thing, but something to investigate and also to kind of get us away from looking at perpendicular bisector, but still being able to utilize the similar ideas of construction. And currently, Joey has his on the screen, and um, just to rephrase, if you don't mind, Joey, that he utilized the two intersecting circles to create a bisector. So where you have a circle that's with a center at the vertex of the two rays forming their angle, that will intersect the two rays in two distinct points. Well, each ray once, and then you can then create circles from those intersection points to the vertex. And where those two circles intersect, um, you can connect that intersection point with the vertex, form a line between those 2 points, and that'll generate a angle bisector, as we can see being recreated. So there's a circle from one intersection point, circle from the other intersection point to the vertex, and then the formulation of you create a segment from the vertex to the intersection of those two circles. Thus, the two angles created there in blue are have the same measure, and it such that it bisects the original angle that was created. Um, so yeah. There is a connection with this idea of utilization of those primitive tools that we can do to create all kinds of different things with just circles and a straight edge. Um, and for for verification, he went ahead and put those measurements on there so we can see that it does in fact have congruent wow, angles there when you come do the angle bisector. Um, yeah, really, really good stuff. Um, I wonder, um, other things that we could potentially like bisect or potentially even trisect. It's actually been found that it's very difficult to trisect an angle um, using a compass and straight edge. It's easier, really. And if the class was entirely in person, we'd operate with folding as well. But it's easier to trisect an angle by folding, paper folding. And these applications of the idea of a lot of geometric structure comes from origami. Um, the art of paper folding can create a lot of very, very symmetric, very, very geometrically true images and not images, but figures just from paper folding. And it uses a lot of geometry to make to understand how that thing works out. Um, so what was kind of I want to make sure we understand where the invariance and what the structure guaranteed, because that's what's really important, what the structure is guaranteeing. When you made your circles from your vertices, from the vertex of the angle, what did that guarantee as it relates to, oh, let's say, what did that guarantee? What measure did that guarantee when you made that first circle?
So I'd say that the first circle, let's see, make a ray. The first circle guarantees that it creates 2 points, the points that connect the leg and the circle I'm making,
Mhm.
one there and one here. And by doing that, I have 2 points that are an equal distance from the vertex,
Yeah.
right?
Yep. And that's important notice. That circle creates the structure of those 2 points being equidistant from the vertex. That's an important thing of the structure and the way this was constructed. Um, that it forces this equidistance nature of those two intersection points. And then what was guaranteed from your for your next two circles?
So my next two circles guarantee, let's think about this. The next two circles, their purpose is to create this other point that is a fixed distance, and because the circles are specific, have the same radius as the original circle, they are the same size. They'll have the same radius everywhere around the circle. So the point at which those two circles intersect is the same, is equidistant from the center of those circles.
Mm.
So we're forming two triangles with equal sides, right? Two congruent triangles, if you will.
Yeah, yes, we are. You
There.
gotta put your closing point. So you gotta go back to back to the beginning.
Like that.
Mhm.
Here.
Indeed. We are creating two congruent triangles. And really, you made a particular interesting structure there. Um, do you recognize the figure that you made in blue?
What, a parallelogram?
It
Or
is.
is
It
it
is a
a
special. Yeah, yes, it's a parallelogram. It's a special type of parallelogram. Um, do you recognize it?
I don't.
You know, it is a rhombus. It's a rhombus. All four sides are congruent. And that stems from the fact that they come from these two congruent circles. And your sides are radii of those two circles. All four sides are two different radii
Hmm.
of those four circles. And so what you've done is given a property of rhombi, a property of rhombus is that the diagonals are bisectors of the angles. Um, that's a property of rhombus that when you have a diagonal, they bisect the angle, and that's that's starting to connect for further stuff. But I mean, this is where these things start to kind of build upon one another. Like, why do I know that in a rhombus the diagonals are angle bisectors? Because it comes back to what is an angle bisector and how is that constructed. Um, that's where this starts to come into play. And so when we start to speak to properties of things, properties of quadrilaterals, we know them from the most primitive of things, just the angles, and how we make angles and how we bisect angles. We can show that we can prove that, and which is what you've done here. You've proven that, which is interesting, which is always nice to kind of prove things we didn't expect to prove. Um, just from playing around and putting some extra stuff on there, we kind of developed something different. And that's some of the beauty that can take place in mathematical exploration, that we can kind of discover new things with our geometry that we didn't plan on. Not necessarily new as far as like you didn't know it's a rhombus. You might just don't may not recall. But it's more like we weren't intending to talk about rhombi, but there it is. There it is. It's a parallelogram, and we have shown a property of rhombuses, which is really neat because we can then speak to how we can, if we were asked to formalize a proof, we could then speak to that. Like how do we know in a rhombus that the diagonal are perpendicular bisectors? Like how do we know that? And there we go. This is how we know that. And you could do the same thing with the other diagonals. You can construct that to kind of show why, if you were to form the diagonal for the other ones, you're going to get a angle bisector there as well. Um, yeah, it will be, but it's not apparent in this picture. But if you were to construct it, then you definitely could do that. You could show it. Um, which is really neat, which is really, really neat. Um, yes, the measurement also gives you more things that we can speak to. So there's all, because then the question was like, well, how do you know they're going to be perpendicular, or how do you know that kind of stuff? And so we can talk about that as well, this perpendicularity of it. But that's for later. We will get to discussions and conversations with quadrilaterals, but it's nice to see that things will start to connect as we get further and further in, with one another. So it's not, you know, not a dead end. We'll get there. It's all gonna come together. Because we don't have any closed shapes that we've spoken to yet. It doesn't seem like it's coming together, but it will when we get the closed shapes. Um, but let's go ahead. If you could give me the screen back, please, sir. We'll go ahead and begin speaking about today's loveliness. So I figure out why my stuff is not moving. Share this. Share. Yeah. So yeah, today we're going to speak a little bit about movement. Movement to explore geometric properties. And when we start speaking about movement, we're talking to transformations. And so it's not really not a trick of anything. It's more of it's the argument. It helps us show things. It gives us structure. It provides geometric structure when we start moving stuff around. So the plan for today, we'll talk about movement. We'll talk about how it relates to structure. When we speak to these rigid transformations, reflection, rotation, and translation, we'll talk about these fixed points and geometric explanations. Take a break because 3 hours is a long time. We'll compare what all of the explanations mean, and so we're actually going to give more synthesis as it relates to this idea of measurement explanation and explanation and a movement based or transformation based explanation so we can speak to what those kind of afford us in our stuff. And then we'll talk about how things have connected or will connect to problem set one. And we'll launch that and I'll send that out via email after class anyway, so you have that. We have like, a good while for that, like a week and a half or so to look at those. But I do want to make sure that it is explicit how things are going to connect to the questions that are on there. So we know where it's coming from. All right. Um, all right. We just did that. We just did that. And I think this is in my notes stuff. I'm on the right slide. I'm on this one. There we go. Movements prefer structure. That's what we're looking for. In which case, I want to put this in the chat. Where's my chat screen? I think I gotta get off. Do I gotta get off here to do that? Probably. Let me stop sharing and put the amplify in the chat. Um, Again, amplify is just the housing of Desmos. Before I speak to what is there. Okay. Um, there's one student. So this first one, this idea of reflection. So just to kind of start it off, there is a figure that is reflected over the green line. The blue, the purple is reflected over the green to create the blue. And I want you to, drag, move stuff around, and then pay attention to ideas about invariance, maybe things about distance, midpoint ideas, or symmetries or corresponding points, all that lovely jazz to then consider the questions that are there. And so I'll give it some time to explore the figure and move stuff around and also answer some questions. So I'll give about 4 minutes to do that to kind of explore, or I guess whenever you get finished writing a few, typing a few things there, Joey. Right, all right, all right, all right. Let us see what we got going on. Oh, I'm still going off. So what I see, what I notice is that we have oh, I don't need to say it, you can tell me. So relationships did you see that remain true after the reflection?
So the first one is I think of is the line segment connections will always remain true. So like if there's a line segment from A to B, then on the image there would be a line segment from A prime to B prime, right? And that'll be the case for all the line segments, not just some of them. Angle measures. An angle measure will always be congruent to its reflection, right? So the angle at C will always be equal to the angle at C prime.
Mhm.
It being reflected doesn't change that.
Right, that's true.
Line segment length. So the line from A to B will always be equal to the line from A prime to B prime, right?
Mhm.
Or the measure of it. Those are the main things I saw that remain true. It's still a triangle, I suppose. That's another one.
Mhm.
Retains shape.
Okay. So I suppose the other question I might have, I'm just sharing your screen. So as you do stuff, we'll just see it. That
Right.
way, anybody who looks afterwards knows exactly what you're referring to. Um, so you said that the angle measures are remain the same. The distance between vertices and between points remain the same. Why is it your stuff that you typed in there should be in there? That's upsetting. Go here. That way I can see it. Um, as it relates to distances being, or what stays the same, what happened if did you happen to drag any of your points to be directly on the line of reflection?
Yeah.
And
You
what
can also
happens
drag
if
it past.
mm,
They just carry on through it.
they carry on through it? What about where its image is when the pre-image is on the line?
If one is on the line, the other is also on the line. The
Mhm.
distance from C to the line is equal to the distance from C prime to the line.
All right. The distance from C to the line is equal to the distance from C prime to the line. So, and and it's the perpendicular distance. They'll make sure that's that is how they calculate distance from one to the other. It's a perpendicular distance. I'll make sure that's there. But that's important that the distance from the image to from the pre-image to the reflection line is the same as distance from the image to the reflection line. And what that also means is points that are on the line remain on the line. Um, so they always remain in the same place. That's one that stays the same. Points on the line remain on the line as they're being reflected over the line. Um, and we said that the line of reflection is kind of like a perpendicular bisector. How do you see, how do you notice this perpendicular bisector nature? Or I guess I could ask, could you put something on your image on your screen to help us see this nature of perpendicular bisectorness between a point and its image?
Yeah. All I'd have to do is at a line segment that connects any point with its image, right?
Mhm. So you added the line or the segment CC prime. Why's my alarm going off again? CC prime, a segment. And how do you know that is a perpendicular bisector? Well, you've already
Mm.
spoken to the bisector part. So the bisector part, you had mentioned that the distance between the line and C has to be the same as the distance between the line and C prime. Because those distances are the same, then that must be going through the middle of the segment CC prime. Did I paraphrase what you said
I
properly?
think so.
Okay. I don't want to put words in your mouth. I'll make sure I'm clear. So then we have the issue of this perpendicularity. How do we know that's perpendicular? And I suppose for the purposes of this discussion, we keep in mind that, we can utilize measurement for verification. So if you like to measure to get some verification of this perpendicularity, feel free to do just that.
Oh, hang on, that's not the right angle.
All right. Is it changing? It ain't changing on my screen.
Um, I'm seeing a lot of things I'm doing on my screen that are not on your screen.
Okay. I wonder if I gotta oh yeah, there it is. Gotta load it up again. Oh, that's interesting. Made all the boxes. Um,
Yep,
okay. So 1.57 is the angle measure. I would assume it's the angle measure in radians then. Um,
probably.
so that's a
Half a pi, yeah,
yeah.
3.14.
Would be 2 pi of you're right.
Or a quarter. Yeah,
You're
half a
right,
pi.
you're right. Half a pi. So yeah. Half a pie. So yeah, 1.57 Yeah. So that's your I should have put I didn't know this was in radians, should have been in degrees. But yeah, 1.57 approximately would represent 90-degree angles all the way around. These are all perpendicular and they're such that the line of reflection is essentially a perpendicular bisector of the segment connecting your pre-image and image um, when you undergo the transformation of reflection. Which is nice, and we'll come back to what that does. But yeah, we noticed that reflection preserves distance, it preserves angle measure. Um, I thought at one point I had seen the word orientation. It changes orientation. Indeed, it does. Yeah. So reflection, yes, does change orientation. It kind of reverses orientation. Because what was once on the outside is now, I mean, on the others, on one side is now on the other side. Um, and you says it does not change line segment length effects. Or I assume that that comma is different in two
Yeah.
questions. All right. All right. Sounds good. Sounds good. Sounds good. Now to speak a little bit towards rotation. Same kind of thing. You have this activity and there's a slider for you to change your angle of rotation. And it's gonna be rotating around the point zero. That's your center rotation. And so you can move your center rotation, you can move your image or your pre-image, A, B, or C, and you can move your angle rotation. Um, so I'll give you 4 minutes with which to investigate that, and then we will speak a little bit to it. Suddenly, like thinking about stuff. But we go ahead and speak to things as we continue. Um, so, what stays the same as the figure rotates?
In this case, I would say the orientation of whether it's clockwise or counterclockwise will stay the same, right? So it'll always be from A to B to C to back to A will always be clockwise, whether or not you're talking about the figure or the image.
Oh, okay, I get what you're saying. The naming structure um goes in that direction. Thus, the orientation is the same. I got you. I got you. Whereas in reflection, it goes the other way when you do that
Yeah.
stuff. It'll switch around. If you're going left to right, the letters will switch. So orientation different. I got you. I got you. And what else? What else stays the same as the figure rotates?
So just like before, we keep our segment lengths,
Hmm.
keep our angle measures, we
Hmm.
keep our general shape, right?
Keep our general.
Still a triangle in this case.
Still, yep. In this case, we are looking at a triangle. Still a triangle. Everything else stays the same. Essentially, the sizes, angles, all that good stuff, all your measured ideas, will remain the same. And so, how does changing that angle of rotation affect the image?
Uh, it turns the figure.
Turns it.
I like to also use the term orientation, but the other type of orientation, the other
Mm,
definition of orientation.
right, right.
It always gets me that there are two definitions of orientation. It changes the
Yes.
degrees of the figure.
Hmm. Yeah, I agree. Yeah, the yeah orientation. I like how you put degrees with your orientation because you use it in both places,
Yeah.
which is nice. But yeah, it turns the figure, changing the or I guess the changing the location orientation of it to the degrees as you think of the um center of rotation as an origin. Um, it'll start moving it around, turning it around that particular location. Um, and what about points that are on the center of rotation?
Well, they stay the same, right?
I would hope. Um, you, s- you got a point spinning in a circle. It's still that's it's still itself, still sitting there. And we can actually, I don't know if oh, you're right. Yeah, you put that sucker right on there, and it'll do that. Um, so yeah. And then we have this idea of like what relationships between the figure and its image remain true, and that does speak again to the segment lengths and the angle measures. Those are always going to be congruent with one another. The segments and the angles, their lengths and measures are equal. And how can you tell which points correspond to one another outside of the fact that they're labeled?
Um, you could do if you drew a line from the point to the origin and to another point in the origin from the image, you'd be able to identify which ones are corresponding based on they would have equal measures and lengths of the lines and the angle, respectively.
Oh, could you
Right?
show that? Well, you can't measure in geometry, in Desmos geometry, because that's not enabled about finding the
Right.
measure. But you can measure. I think you can still measure angles. I don't think you can measure side lengths on there. Um, am I currently on your screen? I don't know. Do
Oh,
you
I
see
don't think
this in
you're
your
sharing
screen?
the Desmos.
Oh, I'm not. Okay. What can you see? All right, because it says
I'm
I'm
looking
sharing.
at I'm looking at the slides. Looks like
Oh,
you're
okay.
sharing the slides.
Interesting. Because it on my screen it said it was sharing your. Just got to share that. Um, oh, you did that. Yeah, if you were to connect the pre-image with its to the center rotation with its image, it'll be the exact same or the angle between them should be the same as your angle of rotation as far as connecting them. And you had mentioned the distance from the point or a pre-image to the center rotation should be the same distance as its image to the center rotation. You say that as well?
Yeah, you'd have to do that. Otherwise, you could technically have 2 points that have the same angle if
If all three are collinear, yeah.
yeah,
hmm Yeah, if all three happen to be collinear, then that would take place, especially when you start dealing with like these triangle features. I mean, this one looks collinear. I don't think the angle measure of A is 72, but it looks like it's very close. Which is forcing this thing to kind of look like A, B, and O are collinear. Um, I don't know. I didn't measure angle O. And really you could change the placement of B just to make sure it's not. You can always move B around. And then
yeah,
they won't be collinear at all anymore anyway. Um, but and then how is rotation different from reflection? How are those things different? And we can kind of speak to the what it is you notice that were preserved or what's changed in either one of those.
yeah. So rotation preserves the clockwise versus counterclockwise orientation, which we said, versus reflection is specifically reverse it exactly once.
Mhm.
Um, so that could define both of them. Uh, and then we said, I mean, I think that's the meat of it, right?
For the most part,
And yeah, and rotations change the other type of orientation. They change the degree orientation, but don't change counterclockwise versus clockwise. This,
yeah, of like the look of the figure with respect to itself. Um, yeah, it does not change that with respect to itself. Um, in rotation. Where things are located with respect to the figure. Um, yeah, I agree with that. I agree with that. So, um, let us then move to speak to. I gotta get off this thing. Do-do-do-do. Translation. I think that should drag you over. Yep. So, same idea. You're given a vector, and you can control the head of the vector to dictate whatever kind of magnitude or direction that you want the vector to travel. And you have your pre-image, which is the blue, I believe, and you have your image, which is the red one. And so you want to move things around, drag it around. You can change your vertices in your blue and see how that affects your red. Um, and just kind of speak to things that kind of stay the same or change and how what the vector is doing and how that's different than reflection and rotation. So I'll give us a little bit of time to do that. Now let's slide on back to the slides so that
do
there won't.
notice that it doesn't give me a box to write in.
It
I'm
doesn't give
checking for
what?
it somewhere else. It doesn't give me a box to write in. But
Oh, that's a error. All right. Well, we're just talking
check
about
it.
it.
Yeah.
Because if I update the whole thing, we got to back out and come back into a different one. Ooh, a star.
All right, I think I'm about ready to talk about it.
Yeah, make sure that your thing is brought up so we can see. All right, is it showing the Desmos?
I think it's loading. There it goes. Yep.
Okay. All right, so what stays the same during the translation?
So I'd say all types of orientation, right? Basically everything except for like absolute position, right?
Hmm.
All of their relative positions stay the same, all the line segment lengths stay the same, all the angles stay the same.
Mhm. Is there a scenario where the absolute position would stay the same?
As long as the vector magnitude is zero, then the image is the same as the image, or the image is the same as the pre-image, right?
Okay.
If the arrow was a nothing arrow, just a dot.
Yeah, just a point. Yeah, the vector had no magnitude. Yeah, you can make them, you could force them to overlap. Yeah, there we go. Um, so you said everything change or everything changes, which means no points stay fixed, less we have this vector that is this has a zero magnitude. Um, and how does that vector control the movement? What is it doing?
It's just applying it to it, right? Each point on the figure, the vector is applied to that point to create a new figure or to create a new point.
Each point is applied. It's almost like well, all these can be represented with function, but every point is went plugged into the this vertex, this vector function, or it's applied this vector motion, and then it's given a new position. So yeah, um, the vector tells you exactly the distance um, or the direction, and then how far you're going to go in that particular direction. And then how is translation different from reflection and rotation?
Well, they each require different input, right? Reflection requires a line of reflection. Rotation requires an angle. And we said translation requires a vector, right? Vector, which is often represented as a coordinate point, but an ordered pair rather,
Could be,
but really it's a vector.
or matrix, yeah. So we can represent, our vectors multiple ways. I'm sure you've done all different kinds of stuff because they vector ideas are really popular in programming.
Yep.
Um, so yeah, yeah. Um, what about as it relates to, well, you already mentioned, but just to make sure it's stated, orientation is preserved with translation. Like there's nothing that changes orientation wise. It's just moved and shifted around, but orientation, everything is kind of exact same place where it was as it relates to in relation to the rest of the figure. There is no turning, there is no flipping, it's just sliding. And that makes it a little different and than the other two where orientation starts to change um, when you reflect and rotate things around. When you start turning stuff or you're flipping things, orientation starts to change. But in translations, that does not take place. So yeah. And then one more we'll speak to. We ain't leave forever. Still got to kind of complete. We still got to complete the ideas about perpendicular bisector. I want to make sure we have a complete thought about that stuff. But we have this. I don't know if it's showing where it needs to. I'm gonna stop sharing and share it again to make sure it's popping up. I don't know if you can see it. Well, you can see your screen, but I want to make sure it's on this one. Um, so we're given a segment AB, or no, A and A prime. We're given a section A and A prime, and we're given the perpendicular bisector. And what is taking place here is A prime represents a reflection of the point A across the line. So instead of this being formulated or constructed via circles, this is constructed by reflection. Um, And then we can speak to what is this giving us? What is this give as far as geometrical structure that's becomes proven based on what we already spoke to as relates to reflection. Um, what attribute of reflection did you mention could earlier when we spoke to that you think applies to this idea of this perpendicular bisector type stuff? You
Do you mean the line of reflection is the perpendicular bisector?
can say that, yeah. Line of reflection is a perpendicular bisector. So what does that mean? Like, what does that give you?
The points that make up the perpendicular bisector are corresponding to each other. They're reflections of each other across that bisector, right?
Hmm. Yes, yeah. Points that are corresponding to one another are reflections of one another across that line of reflection. Um, Now, the idea about the bisector, how do we know, based on what you've already said, how do we know that this line of reflection is a is bisecting this?
We could use point P, right?
You can use point P, sure.
So point P shows that every point across this line that we can drag it to, every point across this line has equal distance, is equidistant from both A and A prime.
And how do you know that?
In this case, I can measure it.
This case you can measure it. Um, the lovely thing about reflection is also modeled really well with just folding. Um, they're going to be upon it. They're going to be right on top of each other. And it's a statement you had made, Joey, earlier that the distance from, let's say in this case, A to the line has to be the same as the distance from A prime to the line because we're just reflecting it directly over the line. In essence, doubling the distance as it relates to A to A prime. Has to go A to the line to A prime, doubles the distance. The line is directly in the middle of that. This lets us know um, for sure that we're going to have a bisector because the distance from A to the line, like you stated earlier, is going to be the same as distance from A prime to the line because they have to be the same on both sides of the line of reflection. Um, and then also you had mentioned earlier that you could show that it's perpendicular. The segment that connects an image and its pre-image and the line of reflection were perpendicular. You showed that earlier when you made the four boxes and whatnot, and they ended up being what is it, 1.57 or whatever it was, radians. That this forces this kind of perpendicularity. And it's always a perpendicular distance. Oh, there it is, positive there. You did it. But yeah, we get that very clearly from reflection without the generation of circles, without we can measure to check, but we recognize that kind of stuff from the fact that reflection preserves distance and it preserves angle. And so those things have to be the same on either side. If you're talking about preserving the angle, do this thing twice, I get the 180 degrees. I get a line. There's the reason why there's a line between a pre-image and its image. It forms a line because I reflected 90 degrees over line of reflection. 90, 90, 180. Or a full pi, exactly. To get from one to the other. I see that, or I can reason that because of what reflection preserves. Reflection preserves angle. It preserves um, distance. All those things can be shown just or can be proven or just spoken to purely off of the idea that a reflection is taking place. A like perpendicular bisector is essentially a line of reflection. And those things are being preserved. Therefore, I can state now, because reflection preserves distance, I know that A to the line and the line to A prime are equal. Therefore, the line is a bisector. Because there's an angle measure of because the distance is always measured perpendicularity. We always measure distance perpendicular to things. That's how we measure distance. Because the distance is measured as perpendicular to from A to line of reflection, 90 degree, or let me go backwards. There is a line that connects A and A prime. 2 points form a line. A line that connects those two things. In order for there to be a line, it has to cross over the line of reflection. There are two parts of that. Those two angles have to be the same because you're over the line of reflection. In order for those two angles to be the same and it to be 180 degrees, those two angles must be 90 degrees. Therefore, this must be perpendicular. So now I have the idea of I know that this line is a perpendicular bisector because of line of reflection and what reflection preserves. We're just sitting there and see if it makes sense, and we can write down this kind of it's not necessarily a proof, but this kind of this reasoning, this deductive reasoning of what's taking place to help ourselves. And I'm gonna shoot you a sheet with which to write some stuff to get things down. But did it make sense the way that was verbalized from a reflection about like how I know purely off of reflection what's taking place?
I think so, yeah. I definitely want to see it written down.
Okay. Okay. That's good. Let me stop this share and get back to my slides. Share this share. All right. And then it's just like a wrap up. I was actually showing these while you're working. We're gonna speak to it, but I want to make sure these things popped up for Liasia. Just these takeaways as relates to these geometric structures. And so, reflections, they preserve distance to angle measure. Every point on the line of reflection stays fixed. The reflection is fully determined by its line. Nothing else is needed to create a reflection besides the line of reflection. That's all we're saying there. Um, rotation. Rotations preserve distance and angle measure. Center rotation is the only fixed point, and rotation is fully determined by a center and its angle, or angle of rotation. And then you have the idea of a translation. Preserve distance and angle measure have no fixed points because everything moves, unless we have like a vector that is a point, which zero magnitude. And the translation is fully determined by its direction and distance. So what I want to share with you is I want to make sure that we're getting to the point of having complete. Why can't I get to the chat from this screen? Here it is. All right. So I'm sharing a document with you. It'll ask you to make a copy to hopefully ask you to make a copy to open.
Yep.
In which case, it's just a way that we can kind of put our thoughts down so we kind of have them. So it's not just pure discussion, that we have conclusive ideas to kind of relate things together. So I will open me up one of these. I don't know if we can. Is it still showing?
I see your slides. Very nice.
Still slides. Okay, so I gotta stop sharing and then reshare this. Oh, that's fun. All right, so now we're here. Sure. All right. So then we can fill this stuff in. We can start speaking to what we're getting here. So what stays the same in a reflection? What can we put in our table?
We said line segments. We said angle measure or line segment lengths, right?
Mhm.
We said angle measures. We said the counterclockwiseness or clockwiseness, the orientation.
See, so it's more like nomenclature orientation. You want to include that. Um, because I hesitate with as orientation as a whole, because orientation changes with this, but I don't mind speaking about the naming convention is going to be the same as far as no. This changes. The nomenclature orientation changes with reflection. Were you talking about
Oh, yeah.
rotation? Okay.
I was thinking of rotations.
Okay. I'll slide that down to rotation. And then what changes, orientation changes, um, under a reflection. Do you agree with that?
Yep.
Mhm. And now what stays the same for a rotation?
All the same things, except it gets orientation as one of the things that retains the nomenclature orientation.
Okay. James here too. Like I was just gonna say like two forms of orientation are changing on for the if I can spell. It's weird to put orientation and then nomenclature orientation. So the nomenclature one changes, and then also the orientation of the actual of the figure. Orientation. Hmm. Um, and translation. What is staying the same? I guess we'll say everything.
Yeah.
Everything stays the same there. You have your segment lengths, which I can't spell, obviously, segment lengths, angle measurements, not angel, angle measures, and orientation. I swear I can type decently, but I don't know what's going on. It's the pressure. All right. And really nothing, oh, yeah, nothing really changed except like the location, but I mean, nothing changes as far as the structure of the shape. All right. And then we spoke a little bit to perpendicular bisectors. And so when you utilize things that we know to speak about perpendicular bisectors. So what relationship between PA and PA prime remained true?
And for that one, they were always equal, right?
Yeah,
The length of
they're
it,
always equal.
the measure.
Measure of PA and PA prime remain equal. Anything anything else between PA and PA prime?
I mean, to talk about like the angle, but
Well, a segment wouldn't have we would need a third point to force an angle. Um, so I guess you started saying like PA, you would then need to probably have to come back across to where um the segment A prime intersects the line of reflection to get a second ray because we don't have two rays to make an
yeah, and
angle.
start talking about using the perpendicular bisector as your other leg of your angle.
Yeah. So we'll leave that one, or we can add something different. I do want to we're going to add in here this thing about defining, because now that we've done that, we're going to use as a question, we're going to use reflection to define. Uh, we'll write it down that way we have this thing kind of written. Um, and why is that the case for every position of P? Why is that always the situation for number two there?
Um, because the distance from any point along the line of reflection and a corresponding point will always be equal to the other corresponding point, right?
Hmm.
And so they're always equidistant.
So you're saying the distance from well, I guess it starts off with this premise. The distance between A
Yeah,
line of reflection is always the same as the distance between A prime line of reflection. And so I want to make sure I capture what you said. Could you repeat?
Honestly, I'm not sure I could. I need to write it out somewhere.
Well, maybe that's a flaw of mine. Do you want to have the time to kind of write your thoughts before I'm like trying to put it on here?
Um, yeah, I suppose so.
Okay. So I'll let you have some time to kind of write your thoughts, and then we'll kind of put this on here. Um,
And this is given that the line of reflection is a perpendicular bisector, right?
given, we'll no, not given that, but you can show that, and we're going to show that in number three. We'll speak to that.
Right.
Okay. And it's more, I think it's more the idea of it. I don't want to take away from your quiet think time because I'm talking too much, but it comes from the idea of, reflection preserves distance. And because it preserves distance, the distance from any image and a point on the line of reflection, will always be the same because the distance between them is going to be preserved through reflection. That's just a property of reflection. Um, and you can think of it as like you could always create a segment from a to any point um on the line of reflection, P. That distance of that length of that segment is going to be preserved on the reflection. Um,
Right.
and so that's how we can say like it's going to hold because under reflection, that length is gonna be preserved. The location of those points, all that's gonna be like what's gonna be oriented the other way, but that's gonna be preserved all the way across. So everything on that line will be preserved. That entire distance will be preserved as we start moving it. This is a bad thing. As you're moving it across, it'll always be preserved because reflection preserves distance. But that's where we're getting at. It
Yeah.
holds for every position of P because reflection preserves distance. Um, And so for whatever PA distance, it's going to be the same for PA prime, because reflection preserves distance. Now let's speak to the idea about reflection through perpendicular bisector. Let us think about that. So I don't know which one you want to get to first, the idea of the bisector. That might be one to start. How do I know
Sure.
the line of reflection is a bisector? And this is what we're going to kind of speak to. How do we know? And I would say this is stemming from this idea of preservation of distance. Um, reflection preserves distance. Reflection preserves distance. And and so what that would mean is the distance from, oh, well, I'll start off. I need to start off by having a segment. If you create a line or create a segment between a point A and its image A prime created by um, reflection. So we got that. We've defined that kind of stuff. We had a segment between point A and its image A prime created through reflection. Because A prime was created by reflection, the distance from A to the line is the same as the distance from A prime to the line because reflection preserves distance. All right.
Right.
Um, the distance from A to the line is equal to the distance from A prime to the line because reflection preserves distance. Are we good there?
Yeah.
All right. Because those distances are the same, the line is passing directly through the middle of them. The line would partition it right in the middle. Um, because the those two distances of the segment are the same. So because those two distances of the segment are, I just said the same. That's poor language. Equal. Because those two distances of the segment are equal, and by distance of the segment I mean A to the line to A prime. Those two things are the same. Therefore, that partitioning by the line reflection has to be in the middle. It has to be through the midpoint, um, which is meaning it's bisecting the segment A prime. Do you agree with that?
Yeah, I do.
Okay. So, how do we know that line of reflection is perpendicular?
Could we use that this what we said about it being a bisector is true for every point in the image, including ones that aren't necessarily connected to the shape, right?
Say that again.
Reflection across a line preserves distance uh, from any point, not just the figures, right?
Yes, any point. Any point on well, I mean, I would say like once you start saying there's another point, that point becomes part of the figure that we're kind of doing. But yeah, anything that's a defined point on one side of the line of reflection is going to also have an image on the other side that's going to be the same distance from the line of reflection.
I don't know how to make the jump and launch to how that proves perpendicularity.
Okay.
It proves
So some of this starts going into the idea of the definition of line. Um, so how do we define a line?
we said it passes endlessly between 2 points.
Um, endlessly. Well, yeah, yeah. The line that travels in two directions, passing through get 2 points. 2 points of the plane. Well, it doesn't matter if the plane. They're going to be planar. Um, also, a line is defined as being essentially, since we like the numbers, we can say 180 degrees. We can form a complete, like a whole line, that is what half a plane, um, 180 degrees, that kind of idea. So I'm gonna start again. I'm gonna create a segment between uh a point A and its image A prime created by reflection. So I'm gonna start there. So I have A prime, and the segment between them that was created. Well, A prime was created by reflection. I've drawn the segment between them. Um, a line a line segment is part of a line, right? I mean, by
Sure.
the name, line is part of a line. A line has an angle measure of 180 degrees. Do you agree with that?
Yeah.
All right. What we also know is that if I were to have a point, um, well, it doesn't really matter, but I'll do it on where's the point on line of reflection P. Do you agree that angle A, I need to define the mid, I need to find the midpoint yet. Line of reflection intersects a a prime at M. You go with that?
Yeah,
All right. Just kind of just naming things so I can use the naming for so I can speak to stuff. So line of reflection
right.
intersects a prime at M. If we place a point, if we on the line of reflection, A M P and angle A M, oh, I'm sorry, A prime M P. Do you agree with
Yeah.
that? Angle AMP and angle A prime MP together make angle AMA prime. Do you agree with that?
Hmm.
Which is that line. Which is 180 degrees, which was already shown from earlier that it's going to form this line. Um, because the line of reflection preserves angle measure, AMP must equal A prime MP. You agree with
Yeah.
that? In order for AMP plus A prime MP, MP to be 180 and AMP to and equal A prime MP, AMP and A prime MP must both be 90 degrees. Um, Perpendicular finally have a 90-degree angle. Therefore, the line of reflection is perpendicular to segment AB or A prime. Does that, does that,
Yeah. And
does
at that
that
point,
logic? So what?
yeah. So at that point, we have both proven it's perpendicular and it's a segment. It bisects.
Yep. We've
You put
proven
them
it's
together.
bisector. hmm We've proven it's bisector. We've proven it's perpendicular. Therefore, the line of reflection is a perpendicular bisector. We've proven both of those um, through reflection. And obviously, we had to use definitions of lines and some definitions of things to kind of pull stuff out. But from reflection, all from this idea of preservation of distance and preservation of angle measure, they have to be the same. That gives us a lot of this information to do that. Does that make sense?
It does.
Okay. Do you think you could repeat that? Like that the thought process of trying of formulating why these things are perpendicular and why this thing is a bisector from reflection.
I, I could definitely do the perfect perpendicular one because it's fresh in my mind. Um, Bisector one, I'd have to study it a
Okay.
little bit longer.
Okay. What I will say is the logic behind the bisector one is exactly the same. The logic is the same. Um,
Right.
I create this segment. And then I recognize that because reflection preserves distance, this segment equals that segment.
Right. That's right. Yeah, I think I could.
Okay. All right. Um, and the last thing, what does all this stuff have in common? What do these two transformations have in common? Um, the biggest takeaway is that these reflections, they all preserve, and we didn't mention what this thing, but I do want to make sure it's written down. They all preserve structure. Um, all of them.
They're all
From
rigid transformations.
there it is. That's the word. I didn't want to say it, but yes, rigid transformations. Rigid transformations. Um, and by rigid meaning they're going to preserve the structure. The structure is maintained. Whatever you put into this particular function machine, you're going to get the exact same image out of it. They might have moved it around, but the image is going to be the structure of the image is going to be the same. Um, but the segment lengths, angle measures, all that should be remain the same. None of that changes, which is much different than your non-isometric transformations. Um, we good with that?
Yeah.
All right. All right. Let me get back I know I got to stop to go back to the slides. Let me go back to my slides. Um, let's share slides. Share. All right. And then we have this thing. I didn't even mention symmetry. But yes, I forgot to mention symmetry. Reflection preserves symmetry as well. So that's something else we can kind of put on our table that preserves symmetry. Um, acts as a form of symmetry. All right. Did we speak to that? We did that. This is what we should spend that whole time doing. I just kind of just talk things out. Um, but yeah, this takeaway, I do want to make sure that's in there for no purposes. Perpendicular bisector of a segment instead of all point equidistant from the endpoint of the segment. We already talked about that. That's the locus. The locus for perpendicular bisector is that because locus is defined as the conditions for a set of points. So the locus is all points equidistant from the endpoints of a segment. Do you understand the word locus? The
Yeah,
con
we talked about it.
Okay, good. Like if I were to talk about, it's another way of talking about a like a sphere or circles are good to talk about locus. Um, all points equidistant from a point on a plane, circle. All points equidistant from a point in space, sphere. Um, where the locus is the condition, the object is the sphere. So like make sure we're good with that. And then this last thing is I did reflection across perpendicular bisector maps one endpoint to the other while fixing every point on the bisector. Because reflections preserve distance, every fixed point must remain equidistant from the endpoints. Um, because reflections preserve distance. That's the big thing by utilizing reflections to help us prove stuff that preservation of distance. Um, so yeah. Um, why does reflection explain something that measurement alone cannot? Um, I'll let you sit with that and see if we can to write a little bit about why does reflection explain something that measurement alone cannot. Why is my computer getting ready to die? Okay. So I'll give you a few minutes to kind of write a little bit before we get into the break time. I think that's coming up. Yeah, it is. All right. So I'll give you 5 minutes for that, and I will set my timer to really come up with something. Wait, five, start. Okay. I'll stop sharing. these 5 minute quiet time things with my son so he starts to learn how to be still for 5 minutes.
Mm.
This thing goes off when it happens, that that sound, and he just breaks into dance because for 5 minutes he had to sit still, and then he just loses his mind. All right. So, what do you think about this question? Um,
It's a good question. I'd say reflection have rigid constraints, but also aspects that can be generalized.
hmm.
They can be moved for the sake of a proof, while measurement will only represent a single instance or a set of instances, with every aspect rigid.
I like that. The lack of generalizability with measurement is problematic when you have to start defending the why. Because
Right.
once you start moving stuff, it's like, well, now I gotta keep measuring a whole bunch of things, and I can just keep moving it, and then it starts to break down. Um, also think about the idea that symmetry gives you symmetry. Reflection gives you symmetry. It gives you more information about like where things are, um, than just what things are. And I think that's also really good there. Um, where things are located is important when you start speaking to the why that they're going to be the same, you know, not just I got the same number, but like, well, why is it? Because of where they're located. I'm preserving these by either the symmetry or well, yeah, that's it. I can map these things onto one another. Is really nice there, to give you more explanatory kind of power.
It
Um,
does make me think about statistics
mhm.
and how statistics do use measurements as a proof when you have enough evidence, right?
Mhm.
The p equals 0.05.
Oh
Once
yeah,
you dip to below that, you can consider it proof. Although
yeah.
it's just an interesting topic,
Yeah, that's yeah. I had
somewhat
not
adjacent
thought.
topic.
Yeah, I had not thought about the I guess you could say the allusion to statistical inference and the necessary because yeah, you need sufficient data points to make inference or to draw conclusions when you start talking about your p-values and how appropriate your hypotheses and things are. Um I had not thought about that because yeah, they do. I'm not a statistician, so I cannot say I can speak to that stuff, but because that's a whole other area of mathematics statistics is.
Mm.
Um, but yeah, that is a very true statement that they utilize you once you get to a certain amount of data points, you can, for the most part, make a claim that you can back up with the numbers, although there's always a caveat when they speak to
There
that
is
kind of stuff.
technically that chance you're wrong.
Exactly. And just like that's always in it's like, it's true to this extent that I think I know. Um uh, which is one reason why I forget what it's called. I liked when they did a bunch of, I guess it was the randomized samples, and you took like a whole bunch of those random samples, to actually form a conclusion. Is it randomized cluster sampling? Is that what it's called? I can't
Yeah,
remember. Um,
I believe so.
yeah, I have got to get better at stats. I need to. I know that's a big weakness. But I love that because you could then speak to like there is a sample that exists that's not contained in any of this stuff that is probable or it has the probability of occurrence. It might not occur a whole lot, but I mean it's there. And so like we're aware of that kind of stuff. And I think measurement starts to break down to some degree, or there's like there's a margin of error in measurements. When you start speaking to like, even statistical things, there's a margin of error in there. It's like, we're confident to this extent. Not 100%, but we're mostly confident. You can, it's almost like, trust me, bro. Um, for the most part. Uh, and I know like a good friend of mine is big into stats, and he don't like when I refer to stats as like a trust me, bro type science, but but because of the off chance of like you could be wrong and like everything you're saying is great, but then you could also be wrong.
99.95%. chance
Exactly,
of it being
bro.
correct.
So I'm like, that sounds like a trust me, bro. Because for the most part, yeah, but trust me, it's kind of wild. Um, so yeah, this idea of explanatory power of things, how we can difference between like reflection or measurement and then reflection, how I know the distance are the same. I can see that, I can measure it, I can observe it. It tells us true. It doesn't even tell us why, but I can see it. I can verify that. But reflection and the idea of it mapping points to another point, or endpoints to the other endpoint, where everything else on line of reflection is fixed. That's really powerful, because now I can make claims about every single point on that line because I know they're all fixed because reflection fixes every single point on line of reflection. And then the ones that are off, that are not line of reflection, will map exactly to the other one, to itself or to its image, um, whilst preserving distance, whilst preserving angle. That's very structural. I don't, now I can measure obviously to kind of show that, but it gives me the why and it of where how things are taking place, which is really really powerful. And I do want to make sure we kind of gain that kind of understanding of the power of transformations in our explanations, how they can lend themselves to a lot of explanatory power. That measurement, as you stated, like is situational. It's very specific, um, for things. So we're gonna take a pause. We'll take a pause right quick, and we'll come back about 4:50. What is it, 4:41? 4:51. We'll come back and we'll finish this stuff up. We'll kind of talk to what we got left. We'll talk about, yeah, comparing the things a little more, and then we'll speak to the PS1 so I can kind of explain that a little bit. Sound good?
All right, will do.
Thanks. Go ahead and take a break for a little bit. Willow, willow.
Hello, hello.
All right, getting back to it now. I put my stuff back up. Let's see where we at. The break here. Sure. Okay. All right. There. All right. So let us, continue with comparing some of the explanations and speaking to the kind of questions that each one kind of allows us to answer and what they address, just so we understand the ways in which they can either help us, the affordance they provide, and why sometimes utilizing a singular one might be a disadvantage. And so it's not that anything is more better than others, except we're just pretty measuring, but we want to make sure we understand that you can, to form good argument, we should try to have a marriage of things, because they give us a really good affordance to understanding how things are going. Um, So the different kind of geometric explanations that we kind of spoke to, this first one been this measurement based stuff, which is typically what we tend to do in schools. We have students measure things and just say what are the numbers, make sure the numbers are equal, which is really good for just noticing. I mean, it's like you see it, therefore that's what it is. Um, and to be frank, when you speak to I'm not sure if you've learned about levels of geometric thinking, which is done by Van Healy. The first level of geometric thinking, according to him, is and this he and his wife, according to them. So this isn't the words of Dr. Hoyes because I have my own thoughts, but according to them, which is very, very common, the first layer of geometric thinking is purely what you see. Everything is defined based off the visual. Anything outside of that is just not comprehensible. And so we teach that with my son, elementary school age students, where a square has looked the same, rectangle is always the same, always oriented the same way. Triangles tend to always be equilateral triangles when you show them to elementary to small age kids. Um, a trapezoid is a Pizza Hut sign every single time that you show it to show it to a student, before they start getting structure and like those kind of things. But it's specific. It's good for verification. It's good for checking. It's good for conjecturing. It's good for I wonder why, because I see this, and that's where that starts to come to really play. Um, from there, we start thinking about how we build stuff. When we start talking about building and constructing, that goes into a much deeper, a different layer. And I don't like deeper because I don't tend to I find that younger students have deep geometric thought. They just don't have the verbiage yet. And that's what differentiates things. But um, your construction-based thinking is really about all relationships within your figure are encoded in the construction. They're forced in there. They're built to be a particular way. So like when we were constructing or where you constructed your angle bisector, it is that because it's built that way. It's built off the idea of these are going to be the same distance from each other because that's what these circles are meaning. The radii are going to be the same for these two individual circles. Therefore, I'm going to have this equidistant nature of all points on my angle bisector to the two rays that create the angle. Um, all that stuff is built into the structure of the figure. That explanation is very, very powerful. Like I know this to be true because this is how I build it. I built it that way. And that's a very powerful way to explain why something is the way it is, because you constructed it. Um, I guess you can kind of relate it to like the programming things. Like I know why this program happened. So like I remember I had a program in C++. My final project was to make a poker game or whatever. And mine, unfortunately, showed two pair every time it also had four of a kind. And I was like, and I had to go back through. It was like, well, why is it doing this? Because of the way I built it. Like I built it this way, and that's what's happening. There is there is some of my if thens were not working properly, but I built it that way, and that's what's going on. I built this to be an angle bisector. I built this to be a square. I know it's that because of the way it's constructed. And that's a really powerful way of kind of talking about structure and explaining things. Transformations, the idea of explaining things based off of movement, um, really talks about how relationship has to hold in both locations of the particular structure. Um, that movement explaining things about how relationships have to be true based off of how that movement is defined. If I just merely mirror things, I understand or I know that the movement has not changed the structure of the object. If I just turn something, I have not changed the structure of the object. If I just slide it over, I have not changed the structure of the object. Those kind of explanations are also exceptionally powerful to say how I know things are going to be equal or congruent, depending on whether they have numbers or not, um, and how I know they kind of relate to one another. And so that's very, very powerful as well to kind of speak to those things. And so the ways in which we explain our geometry can pull from all this stuff, but we understand that some of them have more power than others. Some of them are more generalizable than others. Construction and transformation based explanations are much more powerful and much more generalizable than measurement based stuff. But for the most part, we can use measurements to help get those thoughts going. Like, I wonder why this is. I wonder what's going on here. Is this always going to be true? What I'm seeing can lead itself towards construction-based and transformation-based explanations. All right, that's my little spiel on that. So I also want to speak to invariance. Where does invariance appear? And so what we're gonna do, or what you're gonna do, we as in you, the royal we, well, no, it isn't, but it'll be like what remains unchanged, what role variance plays. So if I were to give you a particular figure, like let's say a circle, in a circle, what remains unchanged and what role does invariance play? Now, the way in which we can answer that to kind of preface in a circle, every point must be equidistant from the center. That is the idea that's always unchanged. Um, every point be equidistant from the zero. The center, the invariance is that distance. That's what's not changing. That's the invariant idea. Every point equidistant from the circle, that's defining my locus. That's what's unchanging. The role the invariance is playing, I know that the invariance is taking place in there. The invariance is distance. That's that's taking place. Um, Now these are similar. These are ideas that are they're the same. It's just another way of saying the same thing. So if it seems like I'm saying the same thing twice, it's because they are. Um, every point equidistant center, the invariance is distance. So when I say like reflection, what remains unchanged and what role does invariance play in reflection?
Thing. I mean, it'd be distance between two corresponding points, right?
Yeah, you can say that.
If we want to use distance again.
Okay. And it's fine saying distance, 'cause I mean distance is gonna pop up a lot. Yeah, your distance, angles also preserved, angle measures. Um, all the points on the line are fixed. Do you know what I mean by all the points on the line? Like what line?
Along the line of reflection.
Okay, good. I do want to make sure we don't want to forget that part. All the points on the line are fixed, and that's giving us stuff. When I send out the typed up thing for what we did for that activity, I'll kind of clean up the language that's in that because it's kind of ad hoc um, on the fly type stuff. But I'll clean the language, and that idea of points being fixed is really important when you're talking about describing things. Um, but yeah, all points are fixed, and that invariance allows us to speak to a lot of different things. It allows us to speak to this angle preservation that all the points on the line are going to be fixed because that angle, that point, and then another point on this figure creates an angle that's always going to be the same because those points on the line are going to be fixed every single time. That makes sense? So you're thinking.
I think so.
Okay. So it's kind of like if I got a line of reflection, I got a point. This point to this point is going to have, well, I guess you can make this angle here if you want to. These are going to be the same when I come over here because this point
Right.
is always going to be in the same place. It's not moving at all. That makes that
Yeah.
good? Okay.
I do want to talk about the circle. Every point
hmm
is equidistant from the center. Distance is the invariant. Is it? It's weird. It feels weird to me to say distance is the invariant when really it's the fact that distance is the same is invariant or invariable.
It's distance is the same as invariable. So I think I want to go back to one. I think it's going to be a parts of speech question. Um, because this is speaking to the noun invariant Distance is what's not changing. And I think you're saying the same thing, honestly. You're saying distance is invariable. Um, Distance is not changing.
Although for I'm thinking of like different circles
Oh, okay. Well, in a
in
circle,
a single circle.
yeah, in a circle, the
All right,
distance, yeah.
I get you.
Okay, all right, good. Um, all right. The next thing is rotation. What is invariant in rotation?
Um, well, we got distance again. We've got assuming that the rotation measure is fixed, then angles are preserved, right?
Hmm. Yeah,
Um,
angles are preserved in
yeah,
distance. And I guess we're gonna say like, why is that?
I mean, we could probably say something about how every point that makes up those angles are also, because distance is preserved, those points are also preserved, making the angle the same.
The points are yes, because distance is preserved, the position of the points on the figure to the image, those positions are different figure image positions.
Right,
Um, to formulate their angle, something has to be fixed. The fixed part of a rotation is your center of rotation.
right.
That's going to give you this angle from your figure center rotation image forms an angle. Because this thing, center rotation, is always going to be the same, this is forcing preservation of angle.
Yeah, I'm also thinking about the angles that make up the figure itself.
Okay, yeah,
The
yeah.
angles in the figure and the angles in the image.
Yes, yes. Um, that works, that works, that works. Distance and angle is preserved and the center stays fixed. And that's what's giving you this idea of this just preservation of angle. The other thing is translation. Translation is another thing. So what is happening here? What is unchanged and what role does invariance play? Mm,
So in this case, we said that everything stays the same except for absolute position, right?
yeah, yeah. And that's pretty much all we can work with. There's no fixed points, like you said, there's no absolute position. But distance and angle is preserved. Very true. Um, and this thing with your perpendicular bisector, which is a little bit more to kind of speak to. But yeah, there's equidistant nature from 2 points, and you have this invariance in your locus, which is the locus being the perpendicular bisector. That is invariant. Um, that is always going to be in obviously bisecting this in a perpendicular nature. Um, every single time. By just by definition. And every point on there is going to be equidistant from the endpoints of whatever it is bisecting. Um, and that's where all that stuff happens there. Um, let's see. Oh yeah, synthesis and PS1 launch. Speaking to our problem set one. Um, so very briefly, the idea of problem sets that's going to have has sections, and each section is going to speak to things that we've spoken to in class. So there's a section that deals with locus, and I'm going to pull it up in a second, and I'll send it to you after class, but I'll pull it up and we can speak to that. But you have a section on locus ideas, and it'll speak to the ideas of this invariant conditions, things that must be true that satisfy this condition. And that's where what your loci or what locuses are. And I have a construction question on there where you're just asked to construct something, and then what is a construction guarantee? Then you have your transformations. Again, we talked about a lot about reflection transformation or reflection explanation for a transformation as the transformation for perpendicular bisector. And so, how does this transformation actually explain things for all the points? Then you have your generalizability, which we kind of spoke to. That does go back again with your why we can't use purely measurements to talk to things. because we can't generalize measurements like you said earlier. And then, explaining these structural relationships. Um, I want to now pull up I don't think it does. I gotta stop sharing to pick up a new thing, a document. And then I'll speak to this. Zoom share. All right, you see?
Mhm.
All right, so there is the problem set. Um, Thank you AI for making it look pretty because I can't do that. It's a good use of that though, make it look pretty. Um, But it focused on the things we've done in class. Nothing is going to be new. Nothing is should be things you can't pull from off of conversation that you might recall, or the slides, which I'll send you the slides, or anything that we might have done in class. Everything should be things that are just familiar. It's kind of compiling stuff, more or less, with some individual thought in there. There are these foci for what you're going to be working with, whether it's locus and definitions, why constructions work, invariants, and all this good stuff. So it kind of just explains the structure of that. Um, So first one is a constructing perpendicular through a point. We didn't do this specifically, but it builds off of what we've already done. And I recommend kind of work to think about how you can construct a perpendicular to a point. So maybe you might want to draw a segment or a ray, it doesn't matter. And then how can you make a perpendicular through one of your endpoints or any point on that on there. Um, but it does build off of what we've done. And so since you've already had some thought process pertaining to perpendicular bisector and angle bisector, all that stuff is going to come back into play to kind of speak to how you can find a perpendicular through a point. You can talk about why does that happen? Because in the first one, you'll explain steps. How do you know what role is the midpoint reasoning? Again, when playing this construction, um, that'll make sense as you're doing it. And then how is it connected to perpendicular bisector? So it is very directly connected to perpendicular bisector. Um, so you'll kind of speak to how they're connected. And then here you're given some conditions and you need to describe what the object it's defining is. So here's some locus and what is that essentially? And then why does it satisfy that condition essentially? So what is this explaining of all points from a fixed distance? Are all points equidistant from 2 points? All points equidistant from two intersecting lines? Ideally, they're all things we've actually said very explicitly in class, all three of these. So hopefully you remember. If not, you can always go back and look at some things, and then you're kind of comparing the role equidistance plays in that speaking. Um, then this one, which was pretty much prepping for today, explain the angle bisector. So you've already done that, and now it's just kind of speaking to it. So it's going to talk about the construction, it'll talk about why you know it satisfies the conditions, and why points on not on the angle bisector don't satisfy the conditions of being equidistant from the sides of the angle, the two rays that make up the angle. Um, some inverse reasoning. You're told that P satisfies PA equals PB. And now you're going to go backwards to say, must P be on the perpendicular bisector? Which really gets into some of that if and only if type reasoning. Um, is it biconditional? That kind of stuff. Um, so is it if and only if, or is it biconditional? And so we'll explain what your thought processes is. Um, what it means to be invariant. So again, you have your own words, preferably in English, and then we go from there. I say that because I had a friend in high school who used to like writing his stuff in different languages because teachers would say that, or he'd make up his own language. But I put it as an extra thing in there because I have some interesting friends I grew up with. So use reflection to explain. So this is again, it's pretty much what we did in class today. Describing about reflection and how it's speaking to preserving geometric things or geometric structure. What points remain on reflection? None of these things are new. How can you use reflection to explain about perpendicular bisector, which is again what we just did today. Um, how this goes beyond checking things numerically. And so again, that's talking about the reasoning about how the transformation kind of gives you more than what you just have with just measuring. And then kind of extending a little bit. Talking about two triangles are congruent. So what does that mean about transformations? So we didn't talk about triangles specifically, but we have talked about things being equal, therefore things being congruent. So numbers are equal, structures are or figures are congruent. So how do you know, and what is that really speaking to? And then we have this thing. I'm going to send you a construction of a quadrilateral, and then you have to speak to it off of these things. So I'll send that because I didn't link it in. Well, it'll be linked in this document when I send it, but you'll click on that and you'll be able to kind of speak to what things are speaking to each other as it relates to that particular figure. And then I went ahead and gave you properties to speak to, so we don't have to kind of just. Did I think of all relationships that could be? I don't know. So I'm gonna give you the relationships to speak to these, um, so we know when we're done all the things. And then it's going to write a short definition of how invariance helps explains why locus loci work. So the role of the word invariance when you're speaking about in locuses. Loci. All right. And then another one, because we're teachers, it's always good to throw something in there to think about what teachers or students are doing. I recognize this is not a methods class, but we do want to be thinking forward about utilization. Um, you'll choose one of these statements that a student could have said, and then you'll speak to what it is they understand or what you think they understand, what is potentially missing from their understanding or from their representation of their understanding, and then how you could push their thinking further. Um, and this goes into really trying to think about when students speak that we listen, and we've already thought about ways that we can answer them to push them to go more. Which I'm sure you've talked about that with, engaging in good discourse moves and anticipation and all that good stuff. And the same deal. Um, this is more thinking about planning. If you were to plan a lesson around things, and this is starting to get into prepping for the final project, about thinking about how you would plan stuff, how you would create activity that can dig deep into a particular geometric idea. So what's one important geometric relationship students should notice when they explore this, a misconception or incomplete idea they might get while exploring, one way you could push their thinking, how the dragging and movement, essentially utilizing a DGE will help students recognize invariant relationships versus using static diagrams. Um, and that's that. There's the expectations, so we know what we're looking for. Um, and then is how I grade things. So you know everything that should be in there. There's no questions about like what's going to happen. Now, I did mention this in I was talking about syllabus. As teachers, we're reflective practitioners, and I would say we should be the same thing as students. We should reflect, be able to have a chance to kind of correct. And so for your problem sets, I'll provide feedback, and I like giving lots of feedback. So I'll provide a lot of feedback. And so if there are issues or there are things that's like, I want to fix this, I want to change this, you have the opportunity to do that once you receive it. And so when these things are due, I think it's June the 1st. Yeah, due June 1st. I'll try to get it back to you by the next week. That way I have enough time for ample feedback. I think I put it in my syllabus when I'll get it back. I can't remember offhand. But I gave you dates in the syllabus. Like I'll make sure I get it back by this date. So you have plenty of time if you choose to do corrections or not corrections, revisions, I should say. If you choose to do revisions to get that in there and I can get that regraded and stuff like that. Okay.
Right. Okay.
All right. Are there any questions on this or anything that we coming up with this assignment?
Not yet.
Not yet.
But if I
Um,
do, I email you.
that's perfectly fine if there needs some clarity. That's fine. I I do typically expect that students will communicate with one another. So, because like that's silly to not expect that. It's an unreasonable thought process that you're not going to talk to your peers. Um, So please utilize each other if you feel the need to like talk with each other. That's not to say that you're submitting like a single assignment. That would be kind of crazy, but at the very least, discuss if there are things that
Right.
might give you pause. And I'll put that in the email that I sent to you all this evening about this assignment when I send it to you, so you have that. But you'll get that before the end of the evening. So you have the what is it, 10 days essentially to work on it. All right, sound good?
It sounds good.
All right. Um, that is all. Things are much shorter because just you and I speaking with one another. Do you have any not other, but any questions at all about anything, or are we good
Uh,
to go?
3 o'clock on Monday, right?
Yes, sir. 3 o'clock on Monday. No, 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 no,
Gotta
no,
double
no,
check.
no, not
No, not
Monday.
3 o'clock.
Not Monday because Monday's Memorial Day.
Okay,
So no class on Monday. We'll see each other again next Wednesday on Zoom
at 3 o'clock.
at 3 o'clock. At 3 o'clock. And
Perfect.
unless one of you all let me know there's a conflict and pushing it back to 6 is what needs to happen, but 3 o'clock will be the plan.
Okay, let's see you at 3 o'clock then
I'll see you
on
at three
Wednesday.
o'clock. On Wednesday, not Monday. Don't go to Duke on Monday.
Alrighty.
All right.
Good luck.
Bye bye.
See you
Have a good
then.
afternoon. Yep.